So the goal of this session is to advocate the use of scripting languages or interpreted languages and help you choose the one that most suits your needs. So if you attended the Fortran session this morning, you realize that Fortran is a compiled language where you have a compiler and you transform the code into something that the machine can understand. And we will see that by contrast, interpreted languages are a bit different. They are not better, but they are complementary, and it's always nice to have one of them in your toolkit. So I will talk about interpreters and compilers and the differences. I will talk about Octave, Python, and R, which are three interpreted languages which are very used in the scientific context. I will talk a bit about the graphical user interface and what we call literate programming, where you will see that there are tools that exist in each of those languages to allow you to create dynamic documents where you can have text and then some equations or computations that refreshes automatically when you change some parameters. And then we will talk a bit about additional modules or packages or libraries. The name depends based on the language, but basically the idea is that all of those languages have application stores where you can download and install very easily additional functionalities for the language. And finally, we will see what to do when it's too slow, because it's one of the main advertised drawbacks of interpreted languages is that sometimes they are slow. And then we will see that even if you choose one language and get very good in that language, and then you realize that there's some functionality from another language that you would like to use, we will see that there are bridges connecting the languages. So first, a few words about the difference between a compiler and an interpreter. So, as I said earlier, the compiler is a piece of software that takes the whole text, the whole code of your program, and produces a binary that the CPU can execute directly. Examples include C++, Fortran, Java, Go, Rust, Haskell. I'm sure you know at least some of those. By contrast, an interpreter reads each line of the code and then evaluates it and calls the corresponding functionalities into its own code. So examples include Bash, Python, PHP, JavaScript, Ruby. So this is basically the difference between both. But of course, in reality, the difference is not as clear because there are interpreters that will pre-compile the code. Some compilers compile not to CPU code, but to an intermediate language, which is then interpreted. And there are interpreters for C and C++, which are normally compiled codes, compiled languages, and compilers exist for Python, for instance, which is typically normally an interpreted language. But basically, a common truth is that compilers can apply code-wise optimization. So they have the knowledge of the whole code, so they can use that knowledge to optimize the code much better than the interpreters can do, because the interpreters only sees one line at a time. And they have practically no runtime overhead, because the program that is created only contains the information needed to do what it was intended to do. By contrast, interpreters, they allow easy code introspection, because you can stop the code, you can dive into the variables, values, and see what is going on. And they offer what we call the REPL. So it's a piece of software which reads, evaluates, and prints the result in a loop. So we will see an example like Bash. You tap a command, and then you get the result. They also offer high-level languages and constructs due to the fact that they interpret the language. They are able to do things which are too or nearly impossible for compiled languages to do. Just for instance, the eval function that is available in a lot of interpreters, where you take a piece of code in the language and you evaluate in your script of that language. You cannot do that in Java or in C in general. So the interpreted languages typically are easier to learn because many implementation details are hidden. So in C or C++, when you read data from the disk, you need to allocate space in memory to store that data. In most interpreted languages, you don't have to deal about that. It's all done for you in a transparent manner. They also allow you to share pieces of code very easily. Sorry, to try and test your code easily, because you don't need to go through the whole compile cycle to get your result. You just run the interpreter and then you launch some commands and you directly see the output. It's also easier to exchange and reuse because the scripts are cross-platform by default. When you bring your script to another machine, it's the interpreter that has to be changed, not the script itself. So it's a very nice feature. A Python program running on my MacBook can also run on an Android phone, provided that there's a Python interpreter for the phone. They also offer many simplifications and shortcuts. So as I said earlier, you don't need to manage the memory explicitly. And most of the time they have built-in support for tasks that we perform all the time. So most of the time when you write some piece of software, you need to handle reading and writing files, handling manipulation of dates. You need to create plots, or you need to take care of values that are missing or values that are not a number. In all those interpreted languages, most of the time you have the tools to do the manipulation transparently, and you don't have to put an if statement somewhere if the data is not there and so on. So in the next few slides, I will show you some common tasks and compare how they are done in a typical compiled language and how they are done in a typical interpreted language. So all the comparisons I will do here will be unfair. It's just for the purpose of the illustration. Okay, so if you were there this morning, Pierre-Yves talked a bit about how to parse arguments in Fortran code. So here what you see is a tutorial I found on the internet on how to use the method that he showed this morning to create the code that is necessary to read the arguments in the command line and then give some feedback to the user if the code is not correct and so on. So this is what it looks like. So basically it's 3 screens of code, of Fortran code, just to parse the arguments. And this is how it's done in Python. So in Python, you just use a module called argparse. And then with a few lines like this, what happens is that without you doing anything further, the code comes with everything you need to print a help for the user or to give the user error messages or help messages for all the arguments. And so if the user at some point uses, for instance, --some and then gives some additional information that they should not give, it will have a nice message that explains exactly what is happening, and you don't have to write it by yourself. By contrast, in the Fortran code, where you have to distinguish between the case the user does the correct input and the user gives incorrect inputs. This is another example, is a use and manipulation of XLS files, for instance. You know what XLS file is? A file produced by Microsoft Excel. There are libraries available in C to manipulate and read XLS files. And this is a bit of an example code that uses one library. So the code that you see here is not the code to actually open and read the file, but it's the code to get the content of the file using the library and then writing it in a CSV file, so the comma separated value files. So you see again a few hundred lines, and this is how you do it in R. Simply because there are a lot of details, implementation details that are hidden from you, and you don't have to worry about it. Last example here in Java, how you set up default arguments to functions. You see here a function this with this argument num, where you want to give it a default value. This is how you have to do it in Java. You need to define the function twice. Once where the argument is available and the other one where the argument is not set. It's called overloading in that language. And this is how you do it in Octave. Simply you have one function definition, but if you write it like this, the who argument will have the word value if none is specified when you call a function. Okay, so again, these examples are a bit extremes and not totally fair, but it's to illustrate the point. So the question is, why did I decide to show you those three? So Octave, Python, and R. Well, the reason is that they are all much used in a scientific context. So for instance, R is very strong for statistics. I'm sure nearly all statisticians know at least a bit of R. Octave was initially developed in an engineering context, so it has a lot of features suitable for computations related to engineering. And Python, and especially SciPy and NumPy, are very strong for anything that is related to data manipulation, data science, big data, and so on. In the parentheses here, you see their commercial equivalent, because all of these are free in the sense that you don't have to pay for it, and free in the sense that the code is free and you can open it and modify it. As I write here, actually all these three programs started as wrappers for Fortran code. So they all have the same origin. Some guy somewhere who thought that Fortran was a bit too difficult for their other students or colleagues, and they decided to write code that wraps the Fortran code and then make it easier. And actually, all these in the background, they use Fortran code, and most of the time the same Fortran code actually to perform the computations. So if you multiply two matrices in either of those three languages, behind the scenes, it's a piece of Fortran code that will do the job. By contrast, I list here some other interpreted languages. Ruby and Perl are also used in a scientific context, but with a much smaller communities, more focused on bioinformatics. JavaScript, PHP, Bash, Tcl, Lua, they have a totally different goal, so you won't even be able to represent the metrics correctly in those languages. MATLAB, IDL, and Mathematica are not free, so they are very nice tools, but you have to pay for a license, and most of the time you don't have those licenses available on the clusters. And then Julia is quite a young language. So actually, 3 years ago, I said, well, good luck to get help when you need help. But actually, it's not true anymore. Julia has become much mature, much more mature than a few years ago. And then, so last year I said, okay, it's not true anymore, it's worth considering, but not yet in this session. And actually in this session today, I will show you some bit of Julia. So I'm not an expert in Julia, but I can give you some examples. Do you have any questions about this introduction so far? No? Okay, then I suggest that we have a triple kickstart, actually. So I will show you a few tasks in all three languages to get you a sense of how they work, and in the end, maybe help you choose one that you could learn a bit more in depth. So here, you understand already what I'm showing you. Variable assignment, this is how you say that A is 1 and B is 2 in Octave. In Python, well, in R, you see it's a bit different. They like to be a bit funky. So it's in a row. Right? You can actually use the equal sign, just like in the other languages. But the canonical way of assigning variables in R is with this symbol. I will just try and show you some examples. So I'm connected to the method 3. And I will start Julia. So for that, I load the Julia module, and then I can start Julia. And you see here what I called earlier the REPL. So basically, I have a prompt, and then I can write computations, and then I get the answer. So you see the difference with the compiled language, where you have a piece of code in a text file, you compile it, you run it. Here directly, you can do that. And so here, if I assign variables, I can do it like this. So I assigned 1 to A and 2 to B, and then I asked what is A, what is B, and I get the answer. Okay, so the basic operations are done with the usual signs in all 3 languages, but you see that Python has specific names also available. So you can either use the infix operator, or you can use a function that does exactly the same thing. You see that exponentiation is a bit different in Octave, Python, and R, but the functionality is there and it works the same. To compute the remainder of a division, you see again different names or different operators, but the functionality is there again. In all 3, you can manipulate lists or arrays.
There's a question of Sophie.
I have to read it.
You want me to read it out loud?
No, it's okay. So the question is interesting. The question is, why are compiled languages faster than interpreted ones? Interpreted languages execute the code line by line without going through a compiling step. So why isn't it faster? Actually, when I talk about the speed, I do not take into account the time for compiling, because the time for compiling is done once, and most of the time it's when you have big computations, it's small compared to the time to actually run the computations. So if you do not take into account the time for compiling, that's one point. And the other point is that actually I said earlier that the compiled languages produce code that can directly be interpreted by the CPU, and you don't have the intermediate step of the interpreter that brings a lot of overhead. So it uses more memory. It does a lot of checking of types, of bounds, and so on in the background, so that you don't have to think about it. Because I said earlier, you don't need to think about managing the memory, but it does not mean that it's done automatically. Sorry, it's not magic, it's automatic, but the interpreter has to go through the process of allocating the memory, finding out about the size of the data, trying to estimate the size of the data if it's not known exactly. All things that the compiled language cannot do, but at the same time, so it does not have to go through all those processes. So in that sense, it's simpler, more close to the CPU and the bare metal, and so the overhead is much lower. But we'll see that actually you can compile an interpreted language most of the time, and so everything that I said is need to take care with a pinch of salt. So all 3 languages have way to manipulate vectors and matrices. One important thing for Python is that you first have to import a module. So you need to add a functionality because by default, Python is a generic language that is used to build websites or phone applications and so on. And if you want to use Python in a scientific context, you need to use a specific module. So here, I'm showing NumPy, which is basic low-level matrix operations. And there's on top of that another very used module called SciPy that contains a large amount of mathematical functions that you can use in your computations. So what you see here is a way to write the integers from 1 to 10. Here you have the same thing, but in Python. You see that there's an operator here, but here it's a function. And you see that the bounds here are inclusive, and here the first one is inclusive and the other one is exclusive. You see that R as either the infix operator or the function way of creating an array. And these are variations on these operators that you can use. You can also do the same in Julia. So if I do this, actually in Julia, it does not expand it immediately. So I have to use a collect function, and then I get to see the contents of the array. And then you see in the languages on the slides here, there's a reshape function in Octave. It's also has the same name in Python, and it's called array in R, and it allows you to create a matrix from a vector. So typically when you need to create a matrix, it's often one way to do it is to create the vector, corresponding vector, sorry, and then to reshape it. So here in Julia, I'm reshaping a vector from 1 to 9 in a 3 by 3 matrix, and I get this matrix. Okay, just to show you that the languages come with very low level, well, very first-hand, we call them first-class citizen data structures and operations for matrices and vectors. When you have a vector or a matrix, sometimes you want to extract a part of the matrix or the vector. It is called slicing. And so they all have syntax available for slicing. So this is the way you extract the item at the second line, third column of the A matrix in Octave. The same here in Python, but you see that it's 0 indexed, while in Octave it's 1 index. So the first index, the index of the first element is 1 here, it's 0 here, and it's again 1 here. And you see that there are specific ways to express that you want from this portion to the end and so on. So you can do the same in Julia with, for instance, this, and you get the element on line 2, column 3. So it's see line 2, column 3. It's the 8 here. And so you have also ways to extract the diagonal of the matrix. Here you would write it like this. It's a bit counterintuitive, but there is also a diagonal operator in Octave, and in Julia you need to use a specific module called inner algebra, and then you can extract the diagonal with this simple function. So You've seen that in Python, I had to use import numpy to use a numpy functionality. Here with Julia, I had to use a using keyword with the name of the package to be able to use the function in the linear algebra package. Just like you can extract an element from the matrix by giving the column number and the row number, you can try to find it with either the find function in Octave, it's called which in R, and in Python, it's a bit different. You need to look for non-zero elements, but the ideas are again the same. This is a way to find all the elements of this matrix that are larger than 5.5. This is the same in Python, and again the same in R. And if you want to show it in Julia, it's called find all. And actually, you see the output. So here it's my matrix 3 by 3, and I'm comparing, and you see the dot here. It means that the operator here has to be understood as a element-wise operator rather than an operator on the matrix. If I don't put the dot here, it will try to find a meaning for the matrix operator larger than that can be defined in some context. But here I want an element-wise comparison of the elements of A with this value, and I get the indices of the elements that are larger than 5. And actually, I can use it then to multiply A itself. No, I can't use it. No, I can do something like this. So here I'm multiplying the matrix by a Boolean matrix based on this comparison. And then, so it's kind of a mask that hides the elements that are lower than 5. About control structures, you know what a for loop is and an if statement is. So this is how you write a for loop in Octave. So you can put it in one line or as a block, started with for and finished with end. You see that Python uses indentation to define the scope of the block of the for loop, but you can write it in one line like this. And then in R, you see it's a different approach, yet it's using curly braces to set the scope of the for loop. But then again, you can write it in one line, and most all 3 equivalents here are the same. And you see again that here, because we use the range function, the last element is excluded. So if you want to go from 1 to 5 in Python, you have to write 1 and 6 here. The if statement is written in Octave like this, in Python like this, and in R like this. And you see that in R, there's an if then else function where you can include your if statement in a way into an expression. In Julia, you should be able to do the same. You can write it like this. So you see here that I use a functionality of the interpreter. That way I can look back in the history. So here you have a loop from 1 to 9, and at each iteration I print line I multiplied by itself. So I have the integers from 1 to 81. And the if statement is the same. So here I just showed you a few operations and few ways to manipulate matrices and vectors, just to give you the message that all 3 languages basically have the same functionalities, but they have small variations in the actual syntax. And if you really want a full comparison, you can go to this URL, this website, and you will have a comparison of MATLAB, so Octave, R, NumPy, and Julia for a very large number of operations. And so if you have a look at this, and you don't have a predefined choice, you will maybe find some aspects of some language that you prefer compared to the others, and could help you to choose a language that you want to test. Any questions about this part? So it was very quick. The idea was not to go in deep, but to go in breadth, to show you the different languages and how you can play with it. If there are no questions, I will then show you a bit about the graphical user interfaces and the literate programming, because in most aspects of science, at some point you will want to create a graph or to plot something on a map or something like that. But first, the graphical user interface. So here is a graphical user interface for Octave. And so what you see is a code editor, a window for plots, and you see a Mexican hat plot here. Here you have the window with the interpreter, with the REPL. Here you have either the workspace or the file browser, depending on what you choose. No, sorry, here you have the file browser, so the files in your directory, here there's only one. And here you have the workspace, so the set of variables that are defined currently in the interpreter, and so you can inspect them and see what they are, what their value is, and you can also most of the time edit them with an Excel-like interface. The same exists for R. It's called RStudio, and again you see a code editor, the REPL interpreter here, a space here for graphics and plots. And here you see the workspace. You see here a history tab where you can actually look at your history in RStudio. And so again, the same exists for Python, a bit less used, but it's called Spider. It has the same functionality, so code editor, interpreter, workspace editor, file browser, and so on. Again, for Julia, it's the same. It's called Juno. And you have basically the same functionalities. If you attended the SSH session by Olivier, and you saw that Olivier talked to you about Visual Studio Code, well, there are extensions in Visual Studio Code to actually transform Visual Studio Code into one of those tools, either a Python interpreter or a Julia workspace like this. So it's another option, is to use Visual Studio Code with the correct plugin. So this was for the graphical user interface. So if you like the nice IDE, so integrated development environments, and you prefer that to the rough command line of the clusters, you can always on your laptop install these and then create your program and debug it on your laptop with the graphical user interface, with the plot functionalities, with the debugger, with the workspace explorer. And then when you are happy and you know it works, you just transfer the script to the cluster and you submit a job. And I will show you later on how to submit a job in another session. Any questions about the graphical user interface? No, it's pretty easy. So literate programming, what is this? It's a very old idea, but that has found a very recent implementations. Here you see an example in R with R Markdown. So what you do is you write document, a text here, with pieces of R code inside it. And the structure of the text is Markdown. If you were there at the session I gave two days ago about writing documentation for the software, I told you you should either learn Markdown or RST, and you see that Markdown can be used to write documents like this, where you have a bit of R text, R code into a generic text. And when you put it through knitr or a Markdown, it gives you a web page like this, where you have the text interpreted into HTML, and you have the output of this directly included in your page. Actually, this is an HTML page, but you could produce with the same tool a PDF, for instance. And so you can write your paper and have some equations in there, and then some values for parameters. And then with a click of a button, when you change a value, your paper is modified with the corresponding graph or the corresponding output. The same exists in Python. It's called the Jupyter Notebooks. And if you attended the Fortune session this morning by Pierre-Yves, he actually used Jupyter Notebooks for illustration purposes. So again, you see you have some code here that translates into a web page, an interactive web page where the code is interpreted and the output graphics are inlined with the HTML text. Again, the same exists for Julia. It's called Pluto.gl, and it works exactly the same. You have some text rendered in HTML and then some Julia code that is interpreted and output to the HTML directly. So those are ways to create either HTML or PDF documents that are dynamic based on the values or the code that you put into it. Another way you have to create dynamic website based on data you have is with Shiny, for instance. So Shiny is for R, but the idea of Shiny is that you can create a website, a full website with a lot of options that actually publishes the result of your code. So if you create code, like for instance here to display on the map some data, and you can add some widgets that you can find on any website for choosing a portion of the data or zooming in, zooming out, and so on. Shiny has all the functionalities you need to create this just by knowing a bit of Shiny and a lot of R. So if you have a piece of software, you want to demonstrate how it works and you want to show the result, you can have very nice websites created like this. So Pierre-Yves this morning, he didn't talk about it, but he actually has helped his colleague build a Shiny application where you could see the temperature in a city a few hundred years ago. So, and comparing it with the temperature in the same city nowadays to see the effect of climate change. And so there were sliders where you can go back in the past and see the differences and so on, just with Shiny and a bit of R code. So the equivalent exists for Python. It's called Streamlit. Exactly the same that I told you, but for Python. And also for Julia. There's no equivalent that I know of in Octave. Any question about this? So again, I'm giving you pointers and ideas if there are functionalities you need to, if you want to show off your work. These are nice to know about, and you will have to read the documentation and play a bit with it. But in the end, you will be able to publish your result with a very few time spent organizing things or recomputing figures and including them in the text. It would be all easier. I briefly mentioned in the beginning that all these languages accept extension. So when you have a C compiler, you often have a standard library with it that allows you to allocate memory, stuff like that. But only in C, if you want to compare two strings, you have to write the code that compares the strings. By contrast, Python and many others are said to be batteries included. So whatever you need, you will have it. And most of the time, you will have it in the form of extensions to the language. So in Python, it's called packages. In R, it's called libraries. and in Octave it's called modules. Or the other way around. Actually, in Python, the packages of the modules, and in Octave you can use packages. Well, the name differs. That was what I meant. So if you look at Octave, so we have a Octave Forge, which is like a Google app where you can click to get applications for your phones. Here, it's a website where you can get additional packages for Octave. And the way you get those packages is just like if you are used to using apt-get or apt install on a Debian or Ubuntu machine, for instance, it works the same. Pkg install dashboard image, and this will install the image package into your Octave. And then you will have additional functionalities based on what this package offers. In R, it's called CRAN, so the Comprehensive R Archive Network, and it works the same. If you see on the website that some package offers the functionalities, the function that you need, you can just, in your R code, use install.packages, and then you give the name of the package. And then at the end, you will be able to use the functionalities available here by using the library keyword. So at the beginning of your R syntax or your R code, you will use library and then geonames, and then you will be able to use the functionalities of the geonames package. For Python, it's called PyPy, the Python package index. Again, a website with a large number of packages that you can add. And in your computer, you just use pip. Pip install something. Here, the name is virtualenv. Pip install virtualenv, and then this package is added to your Python installation. And then you can use import in Python to activate, in a way, the functionalities of the package. So I'm guessing that you, yes?
I have a question. So usually there is Python 2 and Python 3, and there's usually pip and pip3. Do we need to use separate build cluster, or do we need to change the module?
So the question is, when you have pip installed in your laptop, if you have Python 2 and Python 3, you will have pip2 and pip3. So on the cluster, if you load the module, the pip command will be the one specific for the Python you loaded. And actually, pip is a bit of a syntax shortcut for Python 2 or 3 -m pip install and then the package. So if you are using the modules that we provide, you just type type pip. But of course, as you are not admins, you will use --user to install it in your own directory, but it should work without thinking about pip2, pip3, and so on. But if you load the Python 3 module and you type pip3, it should work.
And once I install it, and then you can change the module. Another module, back, will installation be prior?
It depends on the way pip works is that it has a different directory for the first minor version. So Python 3.6 and 3.7 have different directories. So if you install in one, you won't get it in the other. But if you install in 3.6.1, it will be available in 3.6.2 if you have both installed. So this was about Python, and again, Julia has the exact same ID. There's a website with all the packages and all the features they offer, and in the Julia code, you can install the package. So here it's a bit truncated, but it says pkg add, and then the name of the package, and then it installs the package and makes it available for you. And you activate the package in a sense using the using keyword, and as I showed you a bit earlier with the direct function, if you remember. So any more questions about this? So there are tips and tricks in the CC documentation on how to add packages to those languages as a regular user. So I said that for pip, you need to use a -- user argument to pip, because otherwise pip will try to install it in a location where you do not have write access. There are other things you need to take into account when doing the same thing in R or in Julia, and it's all explained in the website. So I said earlier, there are general tips that you can follow when you think or you feel that your program is a bit slow compared to what you would expect. And they are actually a bit technical. So I will not go into the details because it would force you to think much more about the inner working of the language, which is one of the opposite direction I want to go by using an interpreted language. The idea is to do not see the details, the implementation details, but being very fast at writing code that works. If you need efficiency, the best way is to link to fast libraries that are themselves written in C++, Fortran, or Java, whatever. So as I said earlier, if you multiply two matrices in Python or in Julia or Octave or R, behind the scenes, it's the either Fortran code of OpenBlast that is used or the C++ code of MKL. But basically the low-level operations that need to go fast, most of the time in the languages, they are already taken from compiled libraries. They all offer some way to include some low-level code written in C inside the language, so you can write your own extensions in a compiled language, optimized language, and then use them in a higher level language. And then you can compile it most of the time with a just-in-time compiler. So, for instance, Python has a PyPy, so PyPy interpreter that has the same functionalities as a CPython interpreter, so the default one, except that it does very clever things in terms of pre-compiling the code before executing it. And then you can go parallel. Actually, all of the languages I've been talking about here have extensions or packages to be able to create parallel code. And for instance, if you attend sessions next week about MPI, you will learn that, for instance, Python has a MPI for Py package that allows you to do exactly the same that you do with MPI in Fortran or C, but with Python. So I'm not talking too much about how to make them fast, because the point of interpreted languages is really to be quick at developing and not necessarily quick at producing the result. And there are ways to create compiled versions of the interpreted languages that can help you go faster. If you attend the session about Python for clusters, you will see some tools that take Python code, which should be interpreted, and compile it into a purely C code, a very fast C code, or Fortran code that can just be run on the cluster as is. So I said also earlier that if you decide to learn Python, for instance, and then you realize, oh, there's this package in R, which is exactly what I need, it's not a problem. Actually, you see here all combinations on how to use R in Python. Well, it's in this project. So you go to the web page, you read the documentation, you install it, and you are able to use R code in Python. Or the other way around. Yes, no, it's correct to use Python in R. This is to use Octave in Python, and you see the list here is complete. So whatever you choose, you will be able to use the packages from another language. So basically, they are fast to learn and they are fast to code. They might be a bit slower to run, but most of the time in the scientific context, you will have a lot of iterations tests and error, and it's very important to be fast at developing. And then when you know what you want, you can go next step into taking your interpreted code and compiling it to make it faster. Are there any questions at this point? Yes.
Bridges, can you say it again?
So the bridges are packages that you can use to make a bridge between two languages. So if you have a Python code, and then you realize that, okay, this function in R does not exist in Python, it is really exactly what I need. Then you by following the correct link here and reading the documentation, you will see a way to use the R code into the Python interpreter.
Just a way to load the function basically in Python from R.
Yes, and also be able to use the R syntax in Python. So now, if you still have time, what I suggest is a small exercise that you can do in any of the languages. If you go to any CC cluster and you look into this path, you will see a list of files, and each file has the same content. Basically, it looks like this. So there's a section header, then a parameter equals something, result equals something, and then meta and time. Okay, we will pretend that they are the output of 100 jobs that have been running on the cluster, where you have been trying to optimize for one parameter. You want to see which is the smallest value among all the possible parameter values. So you run 100 experiments and you have 100 results. And what I suggest is that you try to write the R code or Octave or Python or Julia code to read all those files, extract the contents here, and then try to find the minimum value of result and the corresponding parameter value. The result should be about 5 or 6 lines of code. Something that is important is that this is a structure that is standardized. It's called an ini file. So in all the languages, you will have to look a bit on the internet or in the documentation, but there are ways to parse this without having to specifically say, okay, there's a square bracket and then a name and then something. So there are libraries where you give the path name and it gives you the values here and here directly. So the way it should work is that you will need to read all the files and parse them, and you will have to install some additional libraries. You will build 2 arrays, one with all the parameters that you read and all the values that you read. And then I included some values that are outliers, so very unnatural values that should be excluded from the analysis. And those you can find them with plotting, because it's simply one-dimensional. So you will see that there are numbers you want to exclude. And then we'll find the minimum excluding those numbers. So a bit more detailed, the pseudocode would look like this in all the languages. First, activate the extension for the ini files if necessary. Second, initialize 2 arrays to hold the values, and then you have a for loop from 1 to 99, where you read the file and you store the values, and then you remove from the value the elements that are not correct using slicing, and then try to find the index of the minimum value. And basically, normally, you should be able to do that with simply the comments that are in the previous slides. Okay, I'm going to leave you 10 minutes or maybe 15, it depends on, no, 10 minutes is good. So pick up a language the one that you think you would be more at ease with, and then try to do that. So the first step would be to connect to a cluster and to copy the files that are here into your home directory so you can play with them. And then choose a language, try to find the correct module for the language. So you saw that when I tried to use Julia, I had to look for Julia and then load Julia. Octave, Python, and Julia and R are all available on the method tree. So you can use the method tree if you don't know which to use. And then you can look at the contents and try to look for the correct library and how to install it, and then try to get something that works. And if you have questions, don't hesitate to ask here or to ask in the chat. So you see a solution directory. If you go there, you will get the solutions directly. So if you want to play the game, you should go to Exercice. one additional comment that Olivier did about the speed in Python or Fortran, for instance. There's an advantage of using an interpreted language with a large number of predefined functionalities, so that most of the time they are better written than if you write it by yourself. And it can be that if you write a piece of code by yourself in Fortran, and then you compare it to the same functionality in Python, you could see that the functionality in Python is actually faster because it has been written in a better way by people who have teamed up and gathered to produce the best code possible, while for your case, it could be some 10 lines in a 1,000 line core code where you did not specially optimize that part. Okay, so in the chat, do not hesitate to tell me if you are trying the exercise, and if so, in which language you want to test it, so that I know. At the end, I will give you solutions for all 4 languages. But here in the room, have you chosen the language? Or Python? Okay, there's someone using Python also remotely. So maybe I will spend more time on the Python version. Python is a very, very good choice from the start because it's used a lot and it's a very multi-purpose. But the other functions are, the other tools are also, the other languages are also very nice. But most of the time, it will depend on what your colleagues do and what language they know and in which language the standard tools in your field of application are written. But if you are in a field where the language of choice is PHP, maybe it's time for you to try to push another language for instance. So I will show you the solutions now. If you are not finished and you want to finish by yourself, you can close your ears and your eyes. But here are 3 possible solutions. I will start with the Octave version. So in Octave, there is a init2struct package that you can use. So if you go to that website, you can download it and put it in your working directory. And it gives you access to this init2struct function. And I will go from the beginning. So here I'm just defining the number of results to be 99 because I have 99 files. And then I will initialize a P array and an R array with 99 elements. It will be a one-dimensional array. And then I have a for loop. In that loop, what I do is first I use the sprintf command to create the name of the file. So there are other ways to do it, but one of the simplest way is to use the sprintf command. So what it does is create a character string with res dash and then %d.txt, and here I is the loop index. So this at iteration 1 will create a string res-1 and so on. If you are done some C or Python or C++ or JavaScript in the past, you should recognize this as a pattern for a syntax string, format string, sorry, where you can format the string using placeholders. So this sprintf will create the name of the file based on the iteration index, and then I use init2struct to get a structure in Octave holding the information in the text. And the information in the text file is then available as a struct called res, and so res.main is the content of the main section. If you look at the content of a file, oops. There is a main section with two elements, parameter and result. And so using init2struct, the res object has a sub-object main, and the sub-object of main is parameter, and the other one is result. Here, what I get are character strings because the file is a text file. So I need to use str2double to cast actually the string into a value and then store it at the ith place in the p vector. Then I do exactly the same with the result in the r vector. And by the end of the loop, I have two vectors, one with all the parameter values in the files and the other with all the values in the file. You see here, I can use the plot command to create a scatter plot of P versus R, and a line plot of P versus R. And if you plot it, you will see something that goes like this, but with some very deep, very negative values. And so with this single line, what I'm doing is that I'm replacing in the result vector all the values that are much larger than the preceding value. So the diff operator here compute all pairwise differences between two consecutive values in the vector. And so if that value is large, it means that I might have an outlier. And here I decide on a threshold, 0.9. And so with slicing like this, I say, okay, all the values in R that are this larger in difference from the previous value, I want you to replace them with not a number to exclude them from the analysis. And then I can look for the minimum of R and get the I and G. So I will be the index in R where the value is minimum, and G will be the value of the minimum. So it's the opposite. I will be the value of the minimum, and J will be the index where the minimum is. And then I can display I and then the value of the parameter where the result is minimum. So maybe I lied when I said it was 6 lines, but not by far. Okay, so again here, if you are using the correct predefined libraries, and you are using the matrix manipulation, slicing, and so on, you can do things very fastly in terms of, for instance, gathering all the results and plotting them and finding the optimal value. Here, the same example in R. So already you see a difference by contrast with Octave, is that I have first to activate, in a sense, the ini library. So the library that allows me to read those ini files. But then it looks exactly the same. I am creating or pre-allocating 2 vectors. I have a for loop, I have a plot function, I have a diff, and then the assignment of not available here is not a number, it's a different representation, but the purpose is the same. And then I'm looking for the minimum, and then I'm looking for where this minimum happens in the vector. Other than that, the read.ini provided by the ini library offers a object from which you see again here, I have main subobject and parameter subobject of the main subobject. You see here there was a dot to express the object of an object, the element of an object, and here it's a $sign. But the information is the same, the way it works is the same. And again here, this is a character string because I've been reading text file, so I need to cast it into a numeric value if I want to be able to compare the values. So how do I do that? Here I use str to double, so string to double. Here it's as numeric. So if you put here something that is not numeric, R will try to extract the numerical value from it. And if that is a string, a character string representing a number, then you will get that number. So the plot function here has one more argument specifying the type of plot. And here I use the min function. You see that the min function here ignores the not a number elements. And here the min function, I need to specify that not available that aramical true. So I'm telling min that I want in a computation to ignore the elements that are not there. Otherwise, it just produces an error, warning that there are some missing elements. But here, I know that there are missing elements. I just want the minimum excluding those missing elements. The Python version, very, very similar. Here, I have to load more packages. You see first, I'm importing config parser. So it's, again, the library that reads and interprets, parses the ini files. I import numpy as np to have access to all the numerical libraries and matrix operations and so on. And then I import matplotlib also. It's a package that offers the plotting functionalities. So this morning you saw in the Fortran session that in Fortran you had to write GNU plot code in your Fortran code to create plots. Here, in all these, you have already packages either built in Octave and R, or the form of additional packages in Python. But other than that, very, very similar. Number of files to read, 2 arrays here initialized with zeros, one for the result, one for the parameters, and then a for loop that goes with the index sweeping the range of those 2 vectors. And then I'm using this object offered by this package to read the file. And it's done in 2 steps here, because I first have to create the object and then read the file. But here again, you see a portion of the code where I need to build the name of the file currently that I want to read. I forgot to say that in R, there is exactly the same as printf function as in Octave. In Python, it's a bit different, and actually there are more and distinct ways to create templated strings in Python. There are 4 ways in Python you can do it. Here is an example which is different, but actually there's a function very similar to this one existing in Python 2. In Python also, I mean, Python 2 and Python 3. Anyway. But here again, I use F, and then I can use the get command. I give the section and the parameter key, the parameter name, and then I put it in this vector, and I cast it to a float because I know it's a text I read, and I want a number because I want to be able to run comparisons. You see here plt.plot, so the plot function from the plt. You see in Python, you can rename the packages when you import them. And then again, here I'm looking at all the values that are suspect. So with the diff function, it has the same name here, the same name here. Does the same thing. If the difference between 2 consecutive elements is larger than 0.1, I want to replace the element with not a number. You see here all the interesting operations and constants are taken from the NumPy package. And then I can print the nan-min. So this is a way to find the minimum in an array, taking into account the fact that there are not numbers in the array, and that is what we want. Just like in R, if I don't put nan here, I use the min function, I will get an exception saying, okay, there are not numbers in the array. I don't know what to do with them. Here you are telling Python to explicitly ignore them. And then the equivalent of which.min or the item here, this is how to find the element, the index of the element that is the minimum in some array. Okay, so always the same. As long as you are using the correct extension, the code is very straightforward, a loop. You read the file, you cast the result to integer, you put in a string, and then you use manipulation, you put in a vector, and then you use manipulations on the vector to filter out some values which you don't want. You are able to plot it, and you can find the minimum and find the corresponding minimum in the other vector. I did the exercise in Julia 2. So again, here using ini file and using plots. So here I have to activate in a way the ini file extension to be able to read the files, and also the plots extension to be able to create plots. But other than that, it's exactly the same. 2 arrays, a loop. First thing is to read the file, and you see here the way the file name is constructed is again different from the others. It's a bit simpler here. It looks like PHP for those who know about PHP. It's just inlining the variable with a $, or in Bash it's the same. And so it refers to this variable here. And then you get the parameter in main and the result in main. You cast them to float and you put them in the vector. And then you have a find all. You see here, the Julia language does not offer the same diff command as the others. So here you have to do it by yourself. But you can do it in one line with slicing. So I'm taking R from 1 to the end -1, and I remove R from 2 to the end. So I'm taking the same vector, I'm just translating by 1, and then I'm subtracting the elements element-wise. And all those whose difference is larger than this, I replace with a not a number. Here, there is no equivalent of find or of minimum or find minimum that manages to handle not a number. So I first replace them with infinite. So I replace all those that are not a number with infinite. So I could have put the inf here directly here. It was just to illustrate that there are other options than just using not a number. And then I can use plot R also to plot the results. And then with the find min, you can find the minimum, the index of the minimum in a vector. Okay, and so to show you, if you want to plot the value, you see that it looks like some nice curve with some noise, and then you have two values which are much different than the others. And so the difference between two consecutive values is larger than 0.1, and so those are removed from the analysis.
So what is the final result?
I don't remember. So it should be something like 0.4, something like that.
Yeah. Actually, when you look at the plot, you can see that you only need to remove the values which are less than 0. So it's not necessary to give the difference.
Yes. Of course, if you are able to plot the file, you have additional information. If the data was multidimensional and you did not have a way to plot it other than all the pairwise possibilities, you would need to find of a typically here what I would do if I did not have access to this graphical representation is compute the standard deviation around the mean and then use a multiplier of that standard deviation to say that okay, these values are much different than the others. But here, of course, if you know the range of valid values, you can exclude them directly. So next time I will try to find another example where we cannot do that. Any other questions? Or remotely? No? So in 5 minutes, I will just conclude. So Octave, R, Python, and Julia are very nice options if you master a compiled language to add a new set of skills to your tool belt, to know a interpreted language that will help you perform like mundane tasks such as I showed here, handling a large amount of files, reading them, parsing them, and so on. They are much more programmer friendly than C++, Fortran, and so on, because you don't have to think about the memory, and you don't have to, for instance, if you want to compare two dates, there's a package or a library or whatever that does date manipulation, so you don't have to think about how to compute the number of days between two dates, for instance. It's all batteries included. You are still able to use fast compiled code. Don't go the other way around. I've seen some colleagues of mine inlining Python code into C++ code. So all the difficult things like reading the arguments, reading the files was implemented from scratch in C++. And then the computation was calling Python programs. So it completely misses the purpose. Use Python or R or whatever to do things that are not exactly computations, and then you can offload the computation to a library that is implemented. So focus on the unsolved problem. You do not want to write the code that compares to dates. Somebody has done it before, and they have done it better than you could ever do, taking into account leap years, leap seconds, and so on and so on. And the fact that the Gregorian calendar was included at some point in the history and so on. So my suggestion is that you try them all and play a bit with them, and then you can choose one and become an expert in that language, and it will be one more skill that you can add to your resume.